Hello, everyone. Today, in our higher structure seminar, our speaker is Haldun Özgür Bayındır. He obtained his PhD from UIC at 2018, and his advisor was Brooke Shipley, and his dissertation title was Topological Equivalences of E-infinity differential graded algebras. Let's welcome him for today's talk.
Okay, yeah, thank you very much for the invitation. It's really great to be here. Last time I was in giving a talk in Boğaziçi University, it was in person. I hope I will be able to do it again one day when I'm in Istanbul. Okay, so the title of the talk, Adjoining Roots to Ring Spectra and Algebraic K-Theory. So the main goal in this work is to understand algebraic K-theory of ring spectra. I will start my talk by giving motivation for algebraic K-theory. This part will be more of a motivation for what's coming next rather than background information. You need to understand what's coming next. So I will be a little vague and, hand wavy. And then I'll provide background on trace methods for algebraic K-theory, which is a program that was developed in order to obtain computational tools for algebraic K-theory. And for all that, actually, for algebraic K-theory, for trace methods, something that's very essential is what we call ring spectra, or spectra, ring spectra. This is basically, spectra is a category that lies in between topological spaces and, say, chain complexes, one can say. That's supposed to be more algebraic and a good setting to study these structures. Brave new algebra it's a saying that comes from the philosophy that we should really be doing homological algebra at the level of spectra. You may or may not believe in that, but that's the philosophy we will be following. And then I will talk about our main results and applications. Okay, so the first definition of algebraic K-theory, what we called the degree 0 algebraic K-theory group of a ring, is due to Grothendieck. He defined, for a given ring A, he considers the monoid of isomorphism classes of finitely generated projective A modules and their direct sum. So this is a monoid under direct sum. And then K0, the degree 0 algebraic K-theory group, is the group completion of PA. Let's do the basic example. Let's say if A is a field K, then K modules is just K vector spaces given by dimension, and addition of dimension. Direct sum of vector spaces correspond to addition of dimension. So as a monoid, PK is just natural numbers given by dimension of vector spaces. And you group complete natural numbers, you obtain integers. And that's the first ever algebraic K-theory computation to be made. K-theory, degree 0 algebraic K-theory, what Grothendieck called algebraic K-theory of a field is just integers. Actually, Grothendieck's applications was to Riemann-Roch theorem. Later, so there's an interesting story here. Grothendieck makes the definition of degree 0 algebraic K-theory groups, but there were no higher K-theory group definition coming from him. And then Atiyah takes this, looking at his definition. Atiyah makes the definition of topological K-theory. And he defines topological K-theory of a topological space by considering vector bundles over that topological space rather than like modules over a ring. And under direct sum, it's a monoid, and then he defines topological K-theory in the same way. But in the topological perspective, it's immediate how to obtain the higher K-theory groups. Basically, K1 of a space would be the K0 of the suspension of the space, for example. there's an obvious way to obtain, by taking suspensions of spaces, there's an obvious way to go to higher topological K-theory groups. Now, Whitehead and Boss later look at this, and by kind of like analogy with that, they define the degree 1 algebraic K-theory group. So by the analogous thing to considering vector bundles over a suspension of a space, they do it, and then they say that, okay, K1 should be the abelianization of the infinite general linear group. And the point is that, I mean, they weren't just making this for the sake of generalization. They had very concrete applications in mind. They proved what's called S-cobordism theorem, which showed that these K1 groups can be used to identify obstructions to triviality of H-cobordisms of closed smooth manifolds. And H-cobordism is a cobordism where the inclusion of the boundaries are homotopy equivalences, basically. So they had this application. And then later, Milner defines the second algebraic K-theory group, which also has a completely algebraic definition, but it's more complicated. His applications were actually to number theory, but at the same time, Hatcher and Wagner show that these second K-theory groups can be used to study the diffeomorphisms of smooth manifolds. Basically, they show that obstructions to certain type of triviality of diffeomorphisms of manifolds lie in these, can be understood using these second K-theory groups. So this is kind of like a very common theme in algebraic K-theory. It's a back and forth between topology and algebra, right? Both in terms of applications and definitions. After this point, there was this effort to define the higher K-theory groups. And what would you like, if you had these definitions available, what would you like the higher K-theory groups to satisfy, right? You would want the higher K-theory groups would be to be compatible with the degree 0, degree 1, degree 2 K-theory groups that are already available. And for instance, if you have an ideal of your ring A, then you would want it to fit into a long exact sequence of this form with these given relative K-theory groups available, right? And so that's kind of the point. And actually there were failed attempts, and it was impossible to define this for a while. Eventually, Coulomb gave the correct definition of higher algebraic K-theory. So I will not be using this definition in my talk, like specifically at any point. But I wanted to show you this definition actually in order to give you a feeling about higher algebraic K-theory, in particular in order to show how higher algebraic K-theory has this very topological nature. So the definition here goes as, you take the infinite general linear group on A, and then you take its classifying space. A classifying space, the way you obtain a classifying space is that you take a contractible space with a free GLA action, and then you take the orbits of that space, okay? And then this plus construction is a construction that Coulomb develops, that it's an interesting construction that keeps homology the same while killing a maximally perfect subgroup of the fundamental group, pi 1. Now, this pi n denotes the homotopy class of maps from n sphere into the space, right? This is the degree n homotopy group. So that's how Coulomb defines algebraic K-theory, higher algebraic K-theory. And it's interesting because it's like degree 0, degree 1, degree 2 K-theory groups are completely algebraic. But it turns out that in order to go to higher algebraic K-theory groups, you really need to start getting topological. So this thing originated from algebra ends up having topological nature. And actually for his definition and for some of the computations, he makes Coulomb wins the Fields Medal actually for this definition and computations. So there's this interesting other connection which shows how algebraic K-theory contains many interesting information while being difficult to compute. It turns out that this Venn-Divier conjecture, which is a heavily studied important conjecture in arithmetics, turns out to be equivalent to the vanishing of these algebraic K-theory groups. Now, algebraic K-theory group of integers, you might think, oh, that should be the easiest case to compute, but actually this is still open. So even, you know, algebraic K-theory of integers actually turn out to be quite difficult. And so this conjecture is still open, for example. And it was pretty clear from actually early computations of Coulomb that K-theory will be quite difficult to compute. And actually his computational approach got kind of like stuck early on, and people had to develop new methods. That's where trace methods, the program trace methods, came into play. But let's keep saying more about algebraic K-theory. So later, Walthausen makes this more abstract categorical definition of algebraic K-theory, which allows one to define algebraic K-theory in a very general scenario. For example, one can define algebraic K-theory of ring spectra, which I'm going to tell you about it in a bit, algebraic K-theory of differential graded algebras, model categories, and so, and topological spaces. And actually, Walthausen's initial interest was due to manifold topology. So he was interested in defining K-theory of spaces. So his main result in this direction, one is his definition, and another is his theorem, Walthausen's theorem, which says that now for a differentiable manifold M, he makes a definition of K-theory of M, and he shows that K-theory can be given of this form. Now, what's on the left is the spectrum corresponding to the topological space M. That's not what's interesting here. That's not what we care about here. What's interesting here is this Whitehead diff of M, what's called the smooth Whitehead spectrum of M. So this spectrum appears as a cofactor in the K-theory of M. And what is the smooth Whitehead spectrum? Smooth Whitehead spectrum is a spectrum built out of pseudo-isotope space of the manifold. So these equivalence classes of diffeomorphisms on the manifold. So it's built out of that, and it contains important information regarding H-cobordisms of the space, diffeomorphisms of the space, and pseudo-isotopy space of the manifold. So here Walthausen basically says that, okay, look, all these interesting topological phenomena like pseudo-isotopy spaces, H-cobordisms, and diffeomorphisms, and we can study all these things from a completely new direction, right? That's what he's saying here. We can study them by considering algebraic K-theory. So that's kind of like the big contribution of this theorem, kind of like a very roundabout approach. And then he says, okay, let's look at K-theory of the point. K-theory of a manifold contains K-theory of the point as a retract, and it's a module over it. And actually, he also shows, besides this theorem, K-theory of the point actually contains a lot of interesting information. But K-theory being K-theory, K-theory of the point also just happens to be extremely difficult to compute. And he says, okay, we should have a program. We should have a program to compute the K-theory of the point. And he sets a conjecture which later is improved by Rognus and Assoni into like a series of conjectures, and which basically these conjectures kind of give a program to compute K-theory of the point by studying familiar ring spectra. And so that's what Walthausen says. We should understand K-theory of ring spectra in order to understand K-theory of a point, which is very important for topology. And that's why when he says, I think, brave new algebra for ring spectra, he says, like, we should start understanding the algebra at the level of ring spectra for this purpose. And basically, this program is based on understanding K-theory of these ring spectra called EN. En are ring spectra that actually originate from formal group laws. So for every formal group law, the high-10 formal group law, there is a way of obtaining a ring spectrum, and En is one of those. Okay, so saying so much about spectra, I should say more, maybe to give you a feeling about spectra. But before I start talking about spectra, I must mention that I don't want to get into like the particular definition of spectra and definition of maps of spectra, because they wouldn't be much helpful. Actually, when you work with spectra, even when you're hands-on working with spectra, most of the time you don't really think about the particular definition. You think about spectra through its formal properties. So that's what I'm going to do. Instead of giving you particular definition of spectra, I will try to give you the formal properties of spectra and give you a sense of what the category of spectra is like, in order to, you know, give you a good feeling of what's going on. So spectra can be thought of as a category obtained from topological spaces by inverting what's called the suspension function on topological spaces. So from a topological space, you can suspend it and obtain its suspension. If you take, for example, n sphere, its suspension will be the n+1 sphere. But this functor is not invertible. It's an endofunctor that's not necessarily invertible. That's not invertible. And if you formally invert this functor, you obtain the category of spectra. And as always, you have a map from, for example, your ring to its localization. You have a functor from topological spaces to spectra, which is called infinite suspension functor, which gives you the spectrum corresponding to a topological space. Okay, one can easily say that this is the main setting for stable homotopy theory for the following reasons. The problem is that, you know, the point is that spectra takes you from topological spaces to a more computable, more algebraic setting, while containing a lot of the complexity of topological spaces. And spectra is more computable and algebraic in many ways. For instance, there are these fiber sequences in spectra, which turn spectra into a triangulated category. So these are triangles in spectra, which generalize short exact sequences of chain complexes. So actually spectra generalize chain complexes. And there's this notion of the quotation mark short exact sequence of spectra, which generalize the short exact sequences of chain complexes. In this way, actually, spectra is some sort of an abelianization of topological spaces, in the way that homotopy classes of maps between two spectra is an abelian group, which is definitely not the case for topological spaces, but for spectra it is. So the homotopy category of spectra, not spectra itself, but homotopy category of spectra is an abelian category. So in that sense, it is some sort of an abelianization. And we also have a notion of homotopy groups for spectra too. For example, the degree I homotopy group of a spectrum can be defined to be the homotopy class of maps from n sphere into your spectrum, I sphere to your spectrum. A good analogy, if you're not very familiar with the topological perspective, actually a good analogy is to think about these homotopy groups in analogy with homology of chain complexes. They do behave that way in many ways. For example, in the generalization of, you know, considering spectra as generalization of chain complexes, homology of chain complexes correspond to these homotopy groups. And these triangles of spectra in these long exact sequence in homotopy groups, just like the way short exact sequences of chain complexes in these long exact sequences in homology. Okay, so this is kind of another way to think about these homotopy groups. Another interesting fact about spectra is that they represent cohomology theories in spaces. If you have a cohomology theory, there will be a spectrum that represents that cohomology theory. If you have a spectrum that represents a cohomology theory. For example, if you take the Eilenberg-MacLane spectrum given by the property of having all of its homotopy groups to be given by integers concentrated in degree 0, so all homotopy groups are trivial except the degree 0 one, then this is a spectrum analogous to Eilenberg-MacLane spaces, basically. And this represents the usual cohomology theory on topological spaces. What does this mean? So if you have a topological space U, then the cohomology of this topological space can be computed as the negative I homotopy group of the spectrum of maps. So there, from between two spectra, there's a spectrum of maps. Spectrum of maps between this spectrum corresponding to U and HC. All right, so this is what we mean by representation. And now let's take another cohomology theory on topological spaces, Atiyah's topological K theory. That's a cohomology theory. There is a spectrum represented in it, and that's called KU for complex vector bundles. So you can obtain topological K theory of a topological space in this way. So there is this thing that for a ring spectrum, topological space, whatever, we think about K theory as a spectrum, and the homotopy groups of that spectrum will be our K theory groups. Now, this is a common theme in homotopy theory. Actually, it's similar to how we calculate X groups, torque groups, and so, right? How do you calculate like X groups? You set up a chain complex, and then the homology of that chain complex is your X groups. So usually you got more than just bunch of groups as your X groups. That's X is really a chain complex, or Tor is a chain complex, sometimes a DGA and so, right? And then the homology of that is your Tor groups. So there's a similar situation actually with homology theories. We don't want to just think about them as bunch of groups. We want to think about them as a spectrum, something with some topological information whose homotopy groups are your K theory groups, okay? And yeah, and that's what we do exactly in these situations too, right? You have these spectrum, and then the homotopy of that spectrum is your cohomology groups, right? So it's the same philosophy. Okay, maybe I should at this point define what a ring spectrum is. I've been saying ring spectra so many times. Now, symmetric spectra is a symmetric monoidal category with an appropriate notion of smash product. So what does this mean, a symmetric monoidal category? It means that there's some operation called smash product, which means from two spectra, you can smash them and obtain another spectrum. X smash Y will be another spectrum, right? This is symmetric monoidal, means that X smash Y is Y smash X. This is associative. And then there is a unit of the smash product, which is the spectrum corresponding to the zero sphere, such that X smash S would be X and all that, right? Actually, so this smash product really originates from smash product of topological spaces, but the correct analogy, I mean, one correct analogy in the way the smash product functions in practice is analogy with abelian groups with tensor product, if you like, chain complexes with tensor product. So that's kind of like the correct analogy when you're really thinking about ring spectra. So what do I mean by this? We can define a ring spectrum to be a spectrum equipped with a map from X smash X to X that satisfies some associativity and unitality conditions. Okay, so this is the way we could define an abelian a ring in the first place, right? We could say an abelian group is a ring if there's a map from A tensor A to A that satisfies associativity and unitality. This is really your multiplication, okay? But the point is that in spectra, we have to be very categorical, and we can't use point set level models, like we can't trace elements and so in your object. So you go very categorically in your definitions. In the category of symmetric monoidal categories, this is just a monoid object in the category of, in the symmetric monoidal category of spectrum. And with the same idea, you can also define what a commutative ring spectrum is. You can define a module over a commutative ring spectrum, algebra over a commutative ring spectrum. All these notions generalize. And actually, this is a common theme in homotopy theory, is to generalize classical notions from algebra by, and many times you can just do this by replacing all occurrences of tensor products with smash products, and like co-products of abelian groups with co-products of spectra. And I'm going to show you a few examples of this through this talk. Now, let's do the first example of a ring spectrum. For a discrete ring R, HR, again, the spectrum defined by the property of having all of its homotopy groups given by R concentrated in degree 0, right? By this property. HR is a ring spectrum. And there's even more. So for example, if you take the algebraic K theory of HR, that would be the same as, so there's a notion of algebraic K theory for ring spectrum, and algebraic K theory of HR would agree with Coulin's definition of algebraic K theory of the ring R. Actually, this functor H here, you can think about it as a functor, and being speaking a little roughly, through this functor H, the category of ring spectra contains category of rings as a full subcategory. Okay, so ring spectra contain all rings and maps of all rings, all maps of rings. So it really generalizes rings. It also generalizes the chain complexes, differential graded algebras. So that's why this is called brave new algebra, because it kind of like generalizes all these notions, and there's even more you can do here. Right, for example, yeah, that's kind of like an interesting thing, like algebraic K theory, the definition of algebraic K theory, like it seems like it's really not possible. And one can actually see that it's not possible to do it in the level of algebra, like in the level of, let's say, chain complexes. You really can prove that you can't do it. But at the level of spectra, you can really come up with the definition of algebraic K theory. As I said, ring spectra generalized, the differential graded algebras. Okay, so let's come to trace methods. Let's talk about trace methods. It's a long-standing program starting I think from late 70s that was developed in order to obtain computational tools for algebraic K theory, which turned out to be very difficult to compute early on. So let's A be a spectrum connective meaning that all of its negative homotopy is trivial. In this situation, we consider the map from A to its degree 0 Postnikov section. So what is a degree 0 Postnikov section? This is analogous to the Postnikov sections of DGAs and spaces. It kills all the homotopy above degree 0. But A didn't have negative homotopy, so when you kill all homotopy above degree 0, then you only have homotopy in degree 0, right? So you obtain an object which has only homotopy in degree 0, and these are precisely the rings inside ring spectra, right? So on the right-hand side, what you obtain is a discrete ring, which is given by pi 0 of A, right? So you're mapping A into a classical ring, basically. In this case, in this special case of Dundas-Goodwillie-McCarthy theorem that we use, it says that there is a pullback square relating topological cyclic homology and algebraic K theory. What does this mean? So there is this pullback square. I'm going to define topological cyclic homology, but so if you look at the bottom row of this pullback square, you got K theory of a discrete ring, classical ring. And let's say we already know this, okay? let's say you already know this K-theory of this discrete ring, TC of this discrete ring. Since this is a pullback square, in order to obtain K-theory of A, and let's say that's what you want to compute, what you really have to do is to compute the topological cyclic homology of A, right? So this pullback square reduces K-theory computations into topological cyclic homology computations, right? And topological cyclic homology is actually a homology theory that was defined in order to have this pullback square. It wasn't a homology theory that was just available. It was defined in order to have this. And in order to define the TC, they first defined topological Hochschild homology, right? So that's where it begins. And topological Hochschild homology is defined to be the topological version of classical Hochschild homology. So let me give you the definition of classical Hochschild homology. If you have a discrete ring A or a field K, then you'd set up this chain complex given by tensor pairs of A. And then the differentials are given in this way. It's an alternate sum of di's, where di is given by multiplying degree I element with the degree I plus 1 element, and then the dn just applies a cyclic permutation and then kills the first two elements, right? And then the homology of this chain complex is Hochschild homology. So you want to do the spectrum version of this. And the goal was to do algebraic K-theory. The spectrum version of this is actually your first thing you do, you replace tensor products with smash products. Instead of an A, you will have a ring spectrum X. But we can't have a chain complex in spectra. Why? Because spectra is not an additive category. The homotopy category is additive, but spectra is not an additive category. So instead, when we resolve things, you know, in algebra, you resolve things using chain complexes. In spectra, we resolve things using simplicial resolutions. Okay, so you obtain this object. It's a simplicial resolution where these maps, basically this is analogous to the way you build a CW complex, a space by attaching cells, basically, right? So this part would be your spectrum of 0 cells analogously. This part would be the spectrum of 1 cells, and the maps would be telling you how you attach these cells together, right? Because what's analogous to resolving a module with a chain complex in topological spaces is to resolve your space using cell attachments, right? So, and these maps precisely correspond to these DIs in here. So that's your simplicial resolution. That gives you the information of your cells and how you attach them. If you really get those cells together and really attach them, you obtain what's called the geometric realization of your simplicial object. And that's another spectrum. And that spectrum in this case is called THH. Okay, THH, topological Hochschild homology of X. And the homotopy groups of that spectrum give you the THH groups. Now there is a circle action on THH. That's where the word cyclic comes from in topological cyclic homology. That action comes from the fact that you can apply, for example, C2 action at this level, right? You can switch factors. At this level, there's a C3 action. You can kind of apply cyclic permutation to these smash factors. And you can keep doing this all the way up. And these actions combine into a circle action. So there's a circle action on THH. And using the circle action, one can define topological cyclic homology as the fiber of a map. Now, the older definition of topological cyclic homology was due to Böckstedt, Hsiang, and Madsen. But Nicolas and Schosse very recently, just 4 years ago, gave a new definition of topological cyclic homology, which says that you can compute topological cyclic homology as the fiber of this map. Okay, so, okay, let me quickly tell you what's in here. Maybe I'll not use all the definitions in detail, but so this is the homotopy fixed points of THH with respect to circle action. It's the topological version, the spectrum version of fixed points in the classical case. This is called the spectrum version of Tate construction, and then you again have fixed points. This map is what's called a canonical map. It comes from the definition of Tate construction, basically. And this map phi p is this Frobenius map on THH of X, which is what gives us its what's called the cyclotomic structure. So there's all the structure. You build this map, and then the fiber will be topological cyclic homology. So if you want to compute K theory these days, what you do is that you first compute topological Hochschild homology, understand these fixed points, understand the Tate construction, understand homotopy fixed points, understand this map, compute the fiber, which is still a very difficult task, but actually it made algebraic K theory computations way more approachable than before. So this is actually a very successful program. Okay, so, okay, going back to the original goal, the goal was to understand K theory of these ring spectra called En in order to obtain K theory of a point. And Assoni and Rugnes actually do the computation for n equals 1, which is still the most complicated K theory computation we have today, at least for ring spectra, maybe not necessarily for rings, but for among ring spectra, that's the most sophisticated computation we have today. For n equals 1, E1 is actually a familiar spectrum. It's the P completion of complex K theory spectrum that I mentioned earlier, representing a TS topological K theory. Now, this little KU will denote the version of KU where all the negative homotopy groups are deleted. Let's just pass on to that. Now, the homotopy ring is given by this graded polynomial algebra. Now, you see, for each I, you have a homotopy group. You can think about this as a graded ring, just like the way you can think about homology of a chain complex DGA, for example, to be a graded ring, right? So it's a graded ring. It's given by this polynomial algebra with a generator in degree 2. This structure comes from like Bott periodicity, that you have this periodic generator and so. Now KU, there's this classical result of Adams that says that KU, P-complete version, splits as a direct sum of suspensions of this other spectrum called the Adams sum. Okay, so what Assoni and Rugnes do, actually, they together first compute the K theory of this Adams sum end, and then Assoni himself on his own computes K theory of KUP. Okay, so, and okay, let's think, and what we really care about is the passage, which was also a very difficult task in the n equals 1 case. It was like a different work of Assoni from the joint work, is the passage from K theory of L to K theory of KU, okay? So if you look at the homotopy ring of KU, that's also a graded polynomial ring, but with a generator in degree 2p minus 2 instead of 2. And if you look at the homotopy rings, homotopy ring of KU can be obtained from homotopy ring of L by adjoining a root to V1. By adjoining a root, I mean in the most primitive sense, which means that you take a polynomial generator and make the power of that generator equal to what you're adjoining a root to, okay? At the level of rings, this is what I mean by adjoining a root. So there is this thing at the level of rings. Assoni and Rugnes, as I say, first compute K theory of L, and then Assoni computes K theory of KU. This T2 star is some sort of an approximation to K theory groups, so let's omit that for now. But the interesting point here is that K theory of KU can be obtained from K theory of L by adjoining a root to another class. Now, this is a very surprised. There are many interesting, surprising phenomena that came out of these computations, like the redshift phenomena, which led to one of the most important open questions in algebraic K theory right now, maybe the most important one. Another interesting phenomena that came out is that why do this root adjunction at the level of spectra end up leading to another root adjunction at the level of K theory? That's very curious, because if you look at the definition of K theory, there is absolutely no reason why it looks like this should be happening. Okay. So that's the motivating result. And the computation of this result is actually extremely complicated, extremely technical, and very, very much very difficult to follow and make sense of. So we try to make sense of this and kind of what's the higher height thing, higher n analogous fact we can obtain compared to this fact in here, right? Because now we have the n equals 2 computation of L. There's like a version of L for n equals 2, but we don't have any other computations in the higher n case. So this is quite stuck. So we try to say something about this passage from L to KU, but in the higher n case. Okay. So what we do is that, I think I'm gonna skip the details here, but the point is, let's go back down to this definition. What we start with is that we construct a method in ring spectra to adjoin a root to a ring spectrum. Okay, that's the first thing we do. It's actually not very complicated, but the point is that if you approach these algebraic K theory questions through here, then many things, so we make this definition, and then a lot of things become much easier, and we get very nice results regarding root adjunction, which lead to results regarding this K theory of En things coming from Walthausen's program. So you adjoin a root and you obtain a new ring spectrum through this definition. And that's a ring spectrum. And the homotopy ring of that ring spectrum is precisely given by root adjunction. Okay. The first thing we show is that, so again, I will not get into details of what this spectrum is, maybe, but this is like the higher height version of L, right? So K theory of En is what we want to compute. And this E bracket N is another spectrum, actually quite a different spectrum. And this is localization. And then this is some sort of coefficient change. But the point is that the spectrum we want to compute can be obtained from this other kind of like simpler spectrum via root adjunction. And another thing is that this root adjunction procedure really takes you from L into KU, all right? Okay, so now we have a new description of this En coming from like Walthausen's program. We want to compute K theory of these guys. And actually, okay, what does this give us? First thing is that it gives us a graded ring structure. Let me tell you what a graded ring spectrum is. You take the classical definition of a graded ring, and you replace all occurrences of coproducts with coproducts of spectra, all occurrences of tensor products with smash products of spectra. That gives you the definition of a graded ring spectrum. Okay, when you work formally, so this basically says that your spectrum splits, and the product takes you from degree I, degree J to degree I plus J, just like a graded ring. And the last condition says that the unit lies in degree 0. This is the classical definition. And actually, when you work with these things, you use a definition that uses functor categories and day convolution, but it's ultimately this, basically. Now, okay, so we're adjoining a root. We did this interesting categorical generalization of this, a different variant of graded rings, basically called mod M graded rings. What happens is that when you adjoin a root to a ring spectrum, you consider your ring spectrum to be in degree 0, when you adjoin a root, you put an element in degree 1, right, to obtain a non-trivial grading. And then the mth power of this root will go back to your ring spectrum, right? But the ring spectrum was in degree 0. So the mth power, but normally lies in degree m, should lie in degree 0. What we do is that you make m equal to 0, basically. So you got to look at mod m grading so that the mth power of the root, which lies in degree 1, will lie in degree 0. So the definition of mod m grading is the graded ring spectrum is exactly the same thing. You just replace z with z mod m. Okay, I think I will skip the details in the slide too, but the point is that there is some sort of an obvious way that there's a canonical, let's say, canonical way that root adjunction results in graded ring spectrum. Okay, and what does this tell us? So these Morava E theories are actual graded ring spectra because they're obtained from root adjunctions. So this is interesting. Actually, how we do this is that we, in spectra, you can't do like point set level computations. What you do is that you show these type of things by setting up obstruction theories, similar to the obstruction theories we have for topological spaces. And I show that the groups that compute these obstructions are trivial. So that's kind of the approach to this theorem. So this actually, Morava E theory being a ring spectrum was this theorem of Hopkins-Miller. It's the known as the Hopkins-Miller theorem. This result improves this theorem, basically. It says that these are not just ring spectra, these are mod p to the n minus 1 graded ring spectra because we adjoin a p to the n minus 1 group. And for example, in the case of Ku, then this is the n equals 1 case. This result says that Ku is a mod p minus 1 graded ring spectrum. In particular, this Adams classical splitting is not just a splitting of spectra, it's a splitting that's compatible with the ring structure that turns Ku into a graded ring spectrum. Okay, so going back to, again, our original motivation, we wanted to compute K theory. For that, we wanted to compute THH. Where did graded ring spectra come from? Why did we care about graded ring spectra? The point is that there's a very canonical way that topological Hochschild homology of a graded ring spectrum splits as an S1 equivariant spectrum into M sum n's. This is, in the classical Hochschild homologies, this is almost like obvious. In topological Hochschild homology, you need to do some infinity categorical considerations very carefully, but it follows in the same way, in the analogy. There's kind of like a very canonical way that this happens. And that's very important for computations because we care about like this S1 equivariant structure on THH, which is very important. So for example, in another work with Tassos Molinos, we use these splittings in order to make the first computation of a K theory of a DGA that is not just a ring. So these splittings are actually very useful for computations. Okay, so what did we obtain? If you adjoin a root, you obtain a graded ring spectrum, therefore THH splits. So our THH here splits in this way. The first theorem we show is that the degree 0 part of the splitting is actually the THH of the ring spectrum you started with. So somehow taking degree 0 commutes with taking THH. This happens if P doesn't divide M. If P divides M, then this is not true, actually. This doesn't get to work. So here I have my assumptions to adjoin a root, but I'm kind of like omitting them, but you need a little bit more about your ring spectrum in order to adjoin a root. But if it's evenly graded and the multiplication is a little bit of commutative, then you can do this. So, okay, the point, and also we also identify the higher, the other summands in the topological Huxell homology. We do this identification by making a new definition of logarithmic topological Huxell homology. And these are also given by the logarithmic topological Huxell homology of X. Okay, but let's go to algebraic K theory. So that's why we were interested. And what happens is that it turns out that this splitting carries all the way to algebraic K theory and gives us a splitting of K theory of X adjoint roots through K theory of X. So K theory of X actually splits K theory of X adjoint root. And up to a Tm+1 equivalence, this is again some sort of height m+1 approximation to K theory. That's actually we always often use in these computations, such approximations. K theory of En in this situation gets to be split by K theory of this other spectrum. This E bracket N is a very different spectrum. So it gets to be split by this other spectrum. So again, this goes back to Asoni's results, how they start with K, in the N=1 case, they start with L and then obtain K theory of E1, right? And the passage was like a very important thing, very difficult thing too. Here we say that in that past, so this spectrum should correspond to the first spectrum you compute in order to compute K theory. And then K theory of En contains this as a summand. So once you do this easier computation, then you would obtain K theory of En up to a certain extent, basically. Okay, so that's one of the applications of our results. Another application of our result is to the K theory of Ku. This goes as follows. So Ku, remember, classify vector bundles of a topological space. And then I told you that Ku has a splitting due to the classical result of atoms, right? Now, K theory of Ku, there is, other than Walthausen's program, there is another reason why we're interested in K theory of Ku. It is because it classifies what's called two vector bundles. So two vector bundles are vector bundles where the fibers are categories instead of vector spaces. So this may sound like a pointless generalization of vector bundles, but it is actually a very meaningful generalization. For example, if you happen to be studying monopoles in physics, then their gerbs are classified by these guys. So this actually is a very meaningful thing to consider. So this K theory of Ku is actually a very important spectrum to think about. Okay, so for Ku, we have the splitting. What about algebraic K theory of Ku? Do we also have a p-1-fold splitting of algebraic K theory of Ku, right? And what we prove, and Asoni computes K theory of Ku, but just the groups. We show here that K theory of Ku also have the splitting analogous to Adams' classical splitting. So K theory of Ku also have a splitting. We identify the degree 0 part as K theory of LP, right? And we also identify the higher ones using Asoni's earlier computations, basically. That's what we do. Yeah. So this gives you the two vector bundle analog of the classical results of atoms, basically. Okay, so I would like to stop here. Ak, if you have a question.
Yeah, but two vector bundles, can you say it again? What was it about?
So yeah, the fibers are considered as, fibers have to be the category of K modules for some K.
Okay, it's not something related to Jervis or Jervis. I don't know.
Well, it happens to be.
Oh, okay.
It's actually if you have a monopole, then the gerbs of that monopole lie in there.
Okay.
It gives you examples of that. I'm not like super. I don't know the physics connections in detail.
So maybe those two vector bundle is like vector bundle analog of where two vector bundle is two vector space introduced by Kapranov and Voivodsky maybe.
Yeah.
That's the like the coordinatized version should be like that.
By the way, there is another form of two vector space, Bayes and Kranz two vector space. Is there any theory like, I mean, a two vector bundle theory using that instead of Kapranov's vector spaces? These are internal, I mean, categories internal to vect. Basically, two vector bundles of Bayes and Kranz.
Yeah, internal category, I think. Vector bundles, category of vector bundles, internal category, which means.
But you mean by Bayes Kranz?
Yeah.
Yeah. The category is internal to vect. The category of internal to category of vector spaces.
Or cross module over vector bundles.
Oh, yeah, maybe.
Whitehead program, algebraic.
So it seems that there is some
program.
I'm sorry.
Sure,
what's that?
Problem. I'm trying to find algebraic Whitehead program.
It seems that there is some philosophical relationship between topology and algebra, right? From your discussion, you consider those, how shall I put it, those spectrums, and you adjoin, for example, some square root of something. It is like extension of algebraic structures kind of thing. So it is quite interesting. I mean, there is this program, arithmetic topology. In fact, one of our speakers was a Japanese mathematician named Morishita. He considers three manifolds, and on three manifolds he constructs inspiration objects inspired from algebraic number theory. And he does class theory, for example.
Yeah. I mean, if you look at these formal group laws, I mean,
yeah, it is local class field theory. The origin of formal group is actually class field theory. That's
kind of like the interest in.
Do you know anything about topological modular forms?
Not much, to be honest. It's not something I spend much time thinking of.
But I believe it is in the same arena, right?
Yes.
Same.
Yeah. It's actually built out of. It's somehow like built out of these ENs, basically.
Okay. So
now it's like you have this moduli state. You have this functor from formal group laws to ring spectra, and then you take some sort of like global sections of this thing, and then that gives you topological. So some sort of global section version of this ENs, basically.
I see. Well, actually, it seems that there is a very big picture a universal laws of mathematics governing almost all branches of mathematics. It seems like that. I mean, a very grand universal law.
Yeah. Somehow, like things get together. Yeah, absolutely. Yeah, I mean, yeah, somehow like these ENs you obtain from formal group law. So what happens is that from a formal group law, you can obtain a homology theory on topological spaces. You can define it by hand, actually, right? By tensoring this very algebraically, but and then you say, okay, this is a bunch of groups, so there should be a spectrum representing this homology theory on topological spaces. And then from that, you obtain the spectrum, right? And then those spectra tend to be very helpful for understanding things like K-theory of a point and so on. Because, and then there's an action on the formal group law, right? The automorphism, if you take the automorphisms of the formal group law, the automorphisms act on the ring spectrum now. And then you take the fixed points of that action, it gives you some sort of a localization of the sphere spectrum. So apparently, so what this is saying is somehow like you can understand all of stable homotopy theory maybe by if you can understand the spectra and its fixed points, basically. The spectra coming from formal group laws and its fixed points. Like sphere spectrum, the homotopy groups of that is the stable homotopy groups of the spheres, right? The biggest problem in homotopy theory, right? And it turns out that, yeah, if you understand this action and the fixed points of this action, then you understand everything about the stable homotopy groups of the sphere, which is very surprising how you can go from the one to the other with such effectiveness and obtain something about spheres. You know?
Excellent. Do you plan to categorify your results also in future, like considering secondary K-theory and so on?
Like the K-theory of the K-theory?
Kind of, I mean, like K-theory of higher categories version.
Yeah, that's not what I've been. I'm more of like these interested in computational aspects of these things on Walthausen's program. So this is kind of like the first part of the program I'm thinking of. The second part will be actually really computing these guys, basically proving the version of Asoni on this thing. Basically, this is adjoining a root to this, right? Now we show that it's a summand, which is actually some sort of there's an open question on whether these things include into fixed points. So we kind of prove one part of that conjecture. Anyway, so this should also be adjoining a root actually. So this should be obtained by adjoining a root to this guy, right? In Tm+1 homotopy.
There is one theorem in algebraic number theory which says that, I mean, if you take a number field and if you consider, let's make it simple, rational numbers, let's say, the field of rational numbers, if you consider its maximal abelian extension, then you can reach maximal abelian extension by adjoining roots of unity. So, I mean, the theorem that you have here states that you have this spectrum and you adjoin the spectrum roots of unity, nth roots of x, for example, right? If you successively continue adjoining, you understand, nth roots or roots of x, for example, eventually you will get some universal spectrum kind of thing.
Yeah, that's something actually is also considered here. You want some sort of, yeah, this maximal extension in ring spectra, but there are kind of problems with that. We're adjoining a root in kind of like a primitive way,
right?
Which is what we were interested for these examples. But you want to adjoin a primitive. We adjoin a root in a plain manner. I want to say. And then there is this adjoining a primitive root of unit, right?
Right.
Which is actually different than what we do. You take a minimal polynomial and you quotient.
Right.
So for that, actually, what's more appropriate is to use some sort of like obstruction theories rather than direct constructions. But there might be a direct construction for that too. And the theory is that there is this result called Suslin rigidity, which is also very interesting, which says that if you take the algebraic completion of FP, K-theory of that is E1, which is like a very surprising result. K-theory of that is E1, which is KU. And then there's this belief that we should be able to have maximal extensions or some sort of algebraic closures of these ENs for which the K-theory will give you EN plus 1.
Okay. Yeah. I mean, excellent. So if Suslin's name is appearing, it has connection with algebraic number theory also.
Yeah, I mean, definitely these are very interesting things. I mean,
yeah, excellent.
Yeah, thank you.
Mehmet, Akif, sen el kaldırdın galiba, değil mi?
Evet. I want to ask, I mean,
bu arada recording'i durdurduk mu? Hala şey yapıyor mu?
Niye durduralım ki? Yani
şu anda recording devam ediyor.
Kalmasın mı? Durduralım dersiniz, durduralım.
Bilmiyorum, fark etmez. Genelde normalde soru kısmındadır diye.
Kaydetmiyoruz.
Sen bilirsin canım, öyle sordum.
Ben açık olarak yani sen ne düşünüyorsun?
Ya, sorun değil. Sen de. Tamam. Ne diyordun Ak?
Bu TC yerine S1 koryant S1 koryant homotopi teori ile alakası vardı ya. Onu compute etmek daha mı zor? Yani TC yerine ona bakanlar var mı ya da oradan yaklaşanlar var mı diye.
Negative TC'yim diyorsun yani
Evet.
S1 fixed points of THH. Ya o da başlı başına bir invariant yani. Hani
yok, direkt yani bu yani TC'nin kendisi tamamıyla S1 koryant homotopi teoriyle çalışılamıyor muydu?
Yok, hayır. O phi p'yi illa gerekiyor. Rationally gerekmiyor.
Rational, anladım.
O cyclotomic structure illa ki yani bunlar ya şu trace methods falan bunlar ya inanılmaz gelişmeler hani so bu phi p initially people do this rationally, right? There is no phi p in that case. TC is just a fixed point. Okay. But in order to do so that's what Goodwill does, and then he says, okay, there should be the non-rational version of this, and we should have all these theories, and then the correct version is basically that there is this Frobenius action in the non-rational case, right? And you need to get rid of this Frobenius in the non-rational situation. And somehow this is getting rid of that Frobenius, basically. You're making it equal to the canonical map somehow, you know?
Okay.
It's like actually getting rid of the structure, right? This whole thing. You take fixed points, you kind of like get rid of the S1 equivariant structure, and then you take phi p minus scan, you get rid of the phi p structure. So you kind of like get rid of the structure and you're left with TC. It's like you can also define it through a universal property. A cyclotomic map from sphere to THH, right? A map that will go into the fixed points because sphere has a trivial action, and then kind of like behave nicely with phi p is precisely what's same as mapping into TC, basically. So yeah. Yeah, so this anyway, so this negative TC, yeah, I mean it's an important object on its own, I guess. I don't know what you can do with it in a non-rational case just on its own. I can't really think of anything like that.
Non-rational case?
Yeah. In the rational case, TC is just this fixed point, right? So,
you may need to maybe consider fixed points of restrictions to finite subgroups of S1.
Yeah, that's what you do actually. In the P-complete case, you can just work with CP.
Because they are the closed ones, otherwise it is, yeah. Otherwise, I mean, any infinite subgroup will be dense. So the closed ones are only finite ones. So you look at cyclic subgroups, cyclic CN equivalent.
Yeah.
Well, it was a very nice and inspirational talk. Thank you very, very much.
Thank you.
So let's thank our speaker.
Thanks. It was a pleasure.